Hello. I hope I'm audible. Can one of you please confirm?
Yes, sir, it's audible.
Yeah, yeah, you're right.
Yeah. So this week's session probably will be short because I mean it's about LDA and PCA mostly, and yeah. So the way the lecture went about, it was like what LDA is, what PCA is, and some features, and starting with K nearest neighbors. So I would primarily talk about LDA, and so for that I found that there was no introduction to any uh, I mean how LDA is actually solved. Basically there was no such introduction in the lecture, so I thought that I would do a very small session. It would be I mean I won't be able to explain all the things because most of them will be outside the course, outside the scope of the course, but I'll still try to give you a brief idea about what is the math behind LDA. Then I have some 4 questions which I have already listed. Somehow this is not okay. I have 4 questions listed here, and I will probably have 1 or 2 more questions on one question I think on PCA, and 1 question on some key nearest neighbors or something. So and then we'll wrap it up. Also, if you have any questions in between, you can stop and ask me. So I'll be happy to answer that. Okay. So LDA, see one.
Bharat,
Hello. Yeah.
sir, we had some questions regarding like previous assignments. So we did
Okay.
raise those issues in the discussion forum, but still, like it
Okay.
seems couple of days before they have released the answers with explanations, but seems they are still, uh,
Okay.
like seems they are like still the issues with the same thing. They are justifying means or they providing explanations for that some of the incorrect answers. So we wanted to see might be if our understanding is wrong or if something is there which we need some correction on NPTEL side.
Okay. So see, one thing is am not. I am part of that course basically, but I have not looked at the discussion forum. So I did not know the questions. I do not know the exact questions that were raised. So maybe if you don't have any issues, then next week I will come back with those questions. If you have doubts, I will try to clear those out.
Okay, sir. Yeah,
Yeah,
that's
yeah,
fine.
yeah,
Thank you.
yeah. Just from my understanding, this is, I mean, the assignment solutions which you are referring to, are they week 1 or week 2 solutions?
So
Or
it is both, sir. In assignment, in week one, I
huh?
think there is like couple of questions, question 4 and 7, which most of us is having issues with.
Okay.
And assignment two, I think there is one question which we feel like it's having issues with.
Yeah,
So I
4 and 7 from assignment 1
four
and
and seven from assignment one and
1.
11 from assignment two.
Okay, I will try
Questions.
to clear these out in the next session. Okay.
Okay, sir. Thank you, sir.
Yeah. Okay, so today's lecture I would be talking about a basic, I mean, see, one thing which I feel is, since this is a basic course on on machine learning, you should at least have a preliminary understanding about linear algebra. So so let's about what eigenvectors are, what eigenvalues are, and all those things. So primarily, um, yeah. So primarily any such, so you can write some. Okay. So you can suppose you have a point in the two-dimensional plane. This is, let's say, 3, and on the x-axis, and let's say this is 2.5. Then generally what you write is, you write this in the form of x-axis first, x value first, and then 2.5. And so this becomes a two-dimensional, you represent every point in the two-dimensional plane in this way. Now this becomes we write that this belongs to R2. Why R? Because these are all real values, and Y2 there because there are two values, right? Now, of course, in machine learning, everything becomes very high dimensional. Of course, you won't be able to visualize those, but in order to abstract them out, you write them in the form of vectors. So these are basically vectors. These are vectors, and you will write something like vector belongs to R of M. So M can be anything. M is a dimension of the vector space. So that is a very simple introduction. And then coming to, now what you can also do is you stack. There is something more deep going on when we write vectors in this form, but let's say you stack these, you stack some two-dimensional vectors in this form, and then this becomes a matrix. So these are all simple stuff. It would be knowing this already. So so we write matrix in the form of, like, this matrix will be in the form of R of 2 cross 3. 2 is the number of rows, 3 is the number of columns. So this is this is a very simple, these are vectors and matrices, just these two things I am introducing. Then coming to another concept which is actually of central importance in both PCA and LDA, is the concept of eigenvalues and eigenvectors. Sorry, there should be no space here. And eigenvectors. So what they basically do is, you have a matrix A, and so this is the definition of eigenvalues and eigenvectors. So you have a matrix A, you multiply that with a vector V, and you get lambda into V. If you find vectors which satisfy this relation, then V is called eigenvector and this lambda is called eigenvalue. And so let's say V is n dimensional. It's a vector, so it's like n cross 1, and V is also, this side is also n cross 1. This is obviously a scalar, so this is 1 cross 1. So this matrix, you can figure out that it has to be n cross n. So one important consideration that you always can keep in mind is, only square matrices have eigenvalues. You will find no rectangular matrices which have eigenvalues. Okay, so this is the, so if you have any more questions on linear algebra, I can of course go through it, but I don't think, so you can ask me, okay, about linear algebra and more questions if you have more doubts about linear algebra. But as of now, this would be sufficient. So then we come to the actual topic of the day, which is linear discriminant analysis, or LDA. See, so you would be knowing that PCA is another very important tool that was taught to you all this particular week. So the basic difference between PCA and LDA is, PCA is unsupervised and this has supervision. This is a supervised algorithm. So the major reason why you use PCA is, you would be using PCA in times like, suppose you have a problem where your feature, the feature on which you will be learning your machine learning algorithm, that is, let's say, 1000 dimensional. It can be the case. It can be even more than that. So in such cases, what you need to find is, of course, if you have to train a classifier which is which is working on 1000 different features, then the classifier will become more complex, right? So there, what you need to find is, can I use a classifier to give me as good a performance as this 1000 I mean, can I use a feature space which can give me as good a performance which is as this 1000 dimensional feature space that you already have. So that is the essence of principal component analysis. And so principal component analysis will take you, let's say, this 1000 dimensional feature space to, let's say, 100 dimensional feature space. Okay, this will I mean, this is the thing that that PCA will do for you, and then you can happily learn a classifier on this 100 dimensional feature space. Your classifier will also be simpler. Now, of course, that is principal component analysis that is still used till date. However, if you know, if you think about it very intuitively, suppose you, apart from principal component, I mean, apart from this 100 dimensional feature space, you also know, somebody comes and tells you that okay, these are your features, and out of all your data points, these are the data points which correspond to class 1, and these are the data points which correspond to class 2. Let's talk only about 2 class classification. So these are the data points which correspond to class 1, these are the data points which correspond to class 2. That extra information that you have, the PCA formulation doesn't have any way to use that extra information. However, that is why people came up with this concept of LDA, because they are now using the class information explicitly, as you will see. Okay, so so that is the essence of that is the reason why people use LDA. So yeah, so let me let me go through the problem setup once, and then we can I'll give a diagram about what LDA basically means. So first thing is, I will be talking about 2 class LDA. Okay, now remember one point, of course, that is the proof of this particular point. I don't think is within, I mean, it was shown also in the class. Always remember that number of classes that is present in the data set equal to C. Let the number of classes that is present in the data set be C. Then maximum dimension space where you can go to is C minus 1. So what does that mean? Suppose you have a 5 class classification problem, then all your vectors, I mean, all your vectors will have what, let's say d dimensions. All your vectors will have d dimensions and 5 classes in your problem. Then d can be less than equal to 4. It cannot exceed 4. Okay, so that is C minus 1. So if it has 100 classes, d cannot exceed 99. So that is the way LDA, that is the constraint that is always there in LDA. So for example, in a 2 class LDA problem, d has to be equal to 1. Okay, so remember this. I will not show the proof of this, but always remember that if the number of classes is if the number of classes is C, then you can go up to C minus 1 dimensions. Okay, so right, so let's say I have n data points. I have points x1, x2 up to xn. Okay, I have n data points, and out of these n data points, there are n1 data points which belong to class 1 and n2 data points which belong to class 2, right? And n1 plus n2 is of course equal to n. Okay, so the LDA problem is all about, and suppose all this x1, x2 up to dot xn, they belong to a R of m dimensional vector space. They are all in R of m, they are in the R of m dimensions. Okay, so basically what you need to do is, you need to find a W you need to find a W such that y equal to W transpose X. Okay, now what is W? W must belong to R of M cross 1 in this case. Okay, W should always be equal to R of M cross 1, and so if you multiply W transpose X, then you basically get a 1 cross 1, you get a point. You get a point, and so finding out this W is your aim. However, which W to find? Now for that, let me show you a diagram. I mean, I'll draw this diagram to the best of my abilities, and then I'll ask you a question. Okay, so let me try to draw the diagram. Yeah, I think this is fine. Okay. Yeah, so suppose this is your class 1 and this is your class 2, and you have two candidate lines. You have this particular line on which you can project these points, and you have this line 1 and you have line 2. Now so there are two candidate points, both of them can be represented by some W, you don't know. Now can somebody say which one would be better for classifying these two?
Line 2, sir.
Somebody has raised the hand. You can, if you are answering the question, you can directly go ahead.
So line 1.
So
Okay.
line 1 I hope.
Okay, so so there was an answer about line 2. Now see what happens is, if you okay, let me draw it here only, that might be easier. Yeah, so if line 1, if you are projecting to line 2, that means that all your class 1 will be more or less here. Okay, and all your line 2 may be more or less here. Okay, so this becomes your class 2 area, this becomes your class 1 area, and this area is common. Okay, this is one situation that you see. If you are going to the other direction, then basically if you are projecting onto this top line, then what you will do is you will project it in this way and you will project this in this way. Now you will see there is a gap between these two classes. Is my I mean, whatever I am drawing is very small, so is this visible to all?
Yes, sir. It's visible.
Yeah, so because of this gap between these two lines, you understand that of course finally your aim would be to classify, right? So if there is overlap between the two classes, then of course you won't be able to learn a linear classifier. But if you project it on this particular line, I mean if you project it on this particular line, then you just learn a linear classifier like this, and on the left side of this would be class 1, on the right side of that will be class 2, and your problem is done, your problem is solved. So line 1 is basically a better option than line 2. I hope it is clear from this diagram. So now that we have established that line 1 is clear, line 1 is better than line 2, we need to come up with a, I mean, of course from the geometry it's good, but what about, I mean, of course this is again in 2 dimensions, right? So we need to come up with a sound mathematical formulation as to what happens when we go on to other dimension, higher dimensions, because that is only when LDA will help us. All these dimensionality reduction techniques will help us, okay? So for that we need to introduce something which is known as the measure of separation. Okay, so what do we mean by measure of separation? Measure of separation is precisely what we mean by, I mean, measure is what we denote by when you, I mean, when you had actually looked at line 1 and line 2, the projections onto line 1 and line 2, you were actually thinking about the measure of separation in mind yourself. Now, one way of, I mean, there can be other ways of looking at this, other ways of formulating this measure of separation, but I will go ahead with the most common way of formulating it. So we will talk about measure of separation being difference of means of the two classes after projection. So after we project all these points, we will calculate the means of both classes, and we will decide on the difference between the two. Okay, that will give us a measure of separation. Of course, if the means are widely different, that means that there is a, I mean, the classes are well separated. If the means are very close to one another, there is a chance that the classes are overlapping with one another. So this is a slightly naive way of doing this, but okay, let's say difference of means of two classes after projection is something that we go ahead with. So again, now I will write this equation once again, w equal to y equal to w transpose x. Okay, this is the projection that you are doing, and w is the matrix that you want, w is the vector, in this case vector which you want to learn. Okay, so mean, so now we have the difference of means of the two classes after projection. So that means we want to find out the mean after we project, right? So when we were in the x dimensional space, I mean when we were in x, I mean we were not projecting it, we were in the original higher dimensional space, then what we had was, we had mean in the x feature space is, let's say, mu I, which is 1 by ni. Ni is the number of points belonging to class 1, class I, and x belonging to class I x. Okay, so this is the class wise mean in the x feature space. We take all the points which belong to that particular class, we sum them up and take an average over the number of points which belong to the particular class in the training set. Okay, this is one. And now, however, we are projecting it, right? So after projecting, what happens? Mean in the y feature space. So I denote that by mu I bar, and that becomes 1 by ni summation y belongs to ci y. Now I substitute y and I write x belongs to ci, and this becomes w transpose x, and this becomes, I can take the w transpose outside. So this is just W times mu I. Okay, so mu I bar is nothing but W times W transpose mu I. Okay, so here what we have thought, okay, we will use the difference of the means of the two classes after projection as my means of separation. So my objective function, so I will solve a problem with the objective as I want to, so this is my objective function. Okay, W is my variable which I want to find out. So all I want to do is I want to maximize this. So I have two classes, so I want to maximize mu1 bar minus mu2 bar. Okay, this is quite simple. I just wanted to, because my means of, here I had written, right, the measure of separation is difference of means of the two classes after projection, and that is what I have written here, difference of the means of the two classes after projection. Very simple. And I now use this formula here, and this becomes W transpose mu1 minus mu2. Sorry, W transpose mu1 minus mu2. Okay, this becomes my measure of separation. Okay, now let me give you a case. Now let's think of another example here. Okay, let it look like this. Okay, and let class 1 be like this, and let class 2 be like this. Okay, I mean by this ellipse by these two these ellipse, I mean that these are the way the points are distributed in class 1 and class 2. Okay, let this be class 1 and let this be class 2. These, I mean, that is the way these points are distributed. You want a two-dimensional plane to come down to a one-dimensional plane, and therefore what you need to do is you need to find out a way in which to project this. Now let's say somebody comes and tells you that your two candidate points would be the x-axis and the y-axis. The two candidate lines on which you can project is x-axis and y-axis. May not be the case, but somebody comes and tells you that okay, these are the two lines that you need to project, that you want to choose between. So suppose you project on the y-axis. So y-axis, the mean of this distribution is somewhere here, and the mean of this distribution is somewhere here, right? So you project all these points here, and the mean gets projected here. This is the mean. So if this is class 1 and this is class 2, this is mu1 bar. Similarly, all these points get projected here, and this mean gets projected here. So this becomes your mu2 bar. Okay. Now this happens when you project on the y-axis. Now let's say you project on the x-axis. Then what happens? All these points come down here, and your mean gets projected here. So now this is mu1 bar, and this gets projected here, and this is your mu2 bar. Okay. Now if you have this objective as your main objective, as your only objective, then what you then can somebody say which one would you select, either x-axis, between x or y-axis?
Y-axis, sir.
X-axis.
Okay, I heard two
Right,
questions.
go for
x-axis.
Go for x-axis. There is an overlapping, no, sir.
Yeah, so you answered it correctly. So what so if you are going through this objective, then you see the distance between mu1 and mu2 is much higher in this case. I mean, of course you have to believe,
okay,
if you have to believe my drawing, but I intended it to in such a way that mu1 and minus mu2 would be much higher on the x-axis than mu1 minus mu2 on the y-axis. However,
Okay, sir.
somebody said that if you are actually projecting on the x-axis, then you see an overlap. This part is overlapped, right? So that means LDA is not working. LDA means you have to separate out the two classes, but with this objective function at least, and you could actually have projected on the y-axis, then both the classes would have been separated. However, because of this objective, your LDA whatever algorithm you will select, that will always select the x-axis for projection, because mu1 minus mu2 is much higher on the x-axis. So we have a problem. So in order to solve that problem, again people needed to come up with solutions. So so the major problem why this is happening here is, you see, class 1 is something like this and class 2 is something like this. So class 2 is actually over a much larger area, it is scattered over a much larger area as compared to class 1. Okay, so this scatter is something which you need to this scatter is something which you also need to take into account while formulating the problem. Okay, so what do you need to do? So the first thing, of course, is you would need to do this. This everybody accepts. I mean, mu1 minus mu2 whole square, you have to increase this. There is no point in not doing that. However, whenever you go for these distances, you also check whether the scatter of these two the scatter of these two classes, they are more or less similar or not. I mean, they are more or less similar means you divide by the scatter of these between each of these classes, so that if one of them, at least any one of them, if any one of them has an unequal scatter, or if they have unequal scatter, then your objective function takes into account the unequal scatter as well. Okay, so for that there is something known as so they introduce something known as scatter, which is s1 square plus s2 square, which is nothing but basically the standard deviation of both these classes. Okay, now I will actually go into some definition. So
Excuse me.
Yeah.
To reduce the scatter, there's square of
yes,
sigma. I mean, standard deviation. Is the way to reduce the scatter. I mean,
no, you can't reduce the scatter. See, scatter is something which is already given to you. Okay, so here, I mean, for example, in this case, the example which I showed, what you needed to do was you needed to do mu1 minus mu2 whole square. Okay, mu1 bar minus mu2 bar whole square. However, you are not subtracting, you are not dividing it by anything, you are just doing this. However, if you project it onto a space where if you see here, okay, now let me draw it again, maybe that would be useful. So this is 1 and this is 1. Okay, now here if you see, the scatter is preserved, right? The scatter of this and the scatter of this is preserved. Am I correct?
Plus on the y-axis also there is a scatter.
No. I'm not talking about y-axis. I'm talking just about x-axis right now.
Okay.
So when you are doing like this, then the scatter for both of these classes, they will be preserved, correct? On the x-axis, right? However, if you come on the y-axis, then you see the scatter of both of them. I mean, I cannot talk about the class 1, but at least for class 2, the scatter has reduced significantly, right? Can you see that?
Scatter has, what do you say?
When you project on the y-axis, the scatter has reduced significantly. Am I correct?
Yeah, compared to the x-axis of class 2.
Exactly. So when your objective function becomes something like this, then apart from this, you're also trying to minimize this. You're also trying to minimize this because only then your final objective function will be maximized, right?
This is not clear.
Yeah, you are maximizing, you are trying to maximize this, right? That is clear. You are trying to, at least you were trying to maximize the distance between the two means. That is clear.
Yeah.
So if you are trying to maximize, now I am saying that instead of trying to maximize the two means, you try to maximize this particular circle thing which I have drawn, which I have written down. Okay. Now that will entail two things: increasing the numerator, which means that move the means as far apart as possible, and also reduce the denominator. Correct? Only then this will try, I mean, any algorithm which tries to maximize this will try to increase the numerator and will try to reduce the denominator.
Yeah.
So if you are trying to increase the numerator, that means you are trying to increase the distance between the means.
Yes.
If you are trying to reduce the denominator, you are trying to reduce the scatter of the projected points. Is it clear?
So that means that S1 square and S2 square,
Huh?
sum is always less than 1.
No.
Subtraction.
No, not necessarily.
Okay.
See,
Because
see,
your,
see,
de- your denominator reduction
Huh?
will be only possible if it is less than 1 in point, in decimal.
No, no, no. See, I am talking about, let's say you have, okay, let me give you an example, a numerical example that might be easier for you to understand. Suppose the numerator is 5, mu1 minus mu2 is 5, so the numerator is 5 square, okay? And suppose you have two candidate values, the s1 square plus s2 square in one, s1 bar square plus s2 bar square in one case is 7, so this becomes 7 square, and in the s1 square plus s2 only is 7, so let's say this becomes 7, and in the other case, this is one example, and the other example, your 5 square is as it is, but instead of 7, this also becomes, let's say, 6. So in these two cases, your algorithm will always choose this one because this has a higher value as compared to this one. I am talking about that.
But you put a plus sign between this S1 square and S2 square.
Right. So what is S1 square? S1 square is this one and S2 square is this one, right? That's a variance of the 2 points of the two projected classes. So I'm not can you tell me your doubt once again? I'm not understanding where you are facing issues basically.
Yeah, because to maximize the difference of the mean, what I understand that increase the denominator. So for that, the standard deviation square has been given. I mean,
yes.
This square plus that square.
Yes.
For the two class 1 and 2. And this value, if it is increasing, in that case, the whole parameter will not be maximized. Because
Yes.
that should reduce so that it will maximize.
Yes.
So in that case, this 5 square by 7, and I understand 5 square divided by 7 plus 6 it should be.
No, I am talking about two different cases where s1 square plus s2 square is 7 in one case and s1 square plus s2 square is 6 in the other case.
That is clear.
So
But this equation.
Right, this one, right. So
Yeah.
you think about these, you think about this diagram only. So in which case would you think S1 square plus S2 square will be more, and in which case it will be less?
S1 will be lower.
Not S1, I am talking about S1 square plus S2 square. So
Oh.
when you project on the x-axis, you get a set of S1 square and S2 square, correct?
Right.
When you project on the y-axis, you get another S1 square and S2 square.
Right.
In which case will the sum be lower?
Some be lower in the y-axis.
So between x-axis and y-axis, which one would you prefer for LDA?
I think y-axis.
Precisely. So do you now understand why this S1 square plus S2 square had to go down in the denominator?
Okay, axis wise you are differentiating.
X and y, the x-axis and y-axis.
Oh, I didn't understand that first. Sorry.
Yes, sir. Yes, sir. Ajit, sir. No. Shall I give my interpretation, sir? I seems to have understood. Please clarify. Okay. See, hello.
Yeah, go ahead.
Yeah. See, we have two classes in this example. The classes could be more also, but in this example, the two classes. Okay. So these two classes can be differentiated either by mean or and the variance. Okay. For example, let us say we are not bothered about variance. We are exclusively focusing on separation by mean. So we will use the numerator, that is mu1 minus mu2 square. Okay. Now, another way to look at it is that the best separation is possible if the variance is low, or variance is low. Variance of each of the class is low. Since we have two classes, so we are clubbing that S1 square plus S2 square. If we have three classes, we can say S1 square plus S2 square plus whatever. So we are considering two factors which will help us separate well. One is mean-based classification. The other one is mean-based separation. Other one is variance-based separation. So in case of mean-based, the mean separation should be high. In case of variance-based, the variance should be less. So when you express in proportionately, it is 1 by S1 square plus S2 square. So both should be there. So that way when you combine both, it says mu1 minus mu2 square divided by S1 square plus S2 square. So this is basically a determinant or a factor which will help separate on both the mean and using mean as well as the variance. Okay, the best classifier, right?
Yes.
So that's what I understand.
Yes. This is correct. So I hope this was clear. So that is why this example, if you remember in mind, this diagram which I showed. So just going by the means, again I will reiterate. So just going by the means, you would have chosen the x-axis, but LDA should choose the y-axis in order to so you can think of, so finally we are going towards the optimization problem. Okay, so optimization problem, always you need to give it some incentive to go to the correct place. In this case, you already know that it is the y-axis. You can see here that at least for this example it is the y-axis. So you need to give it an incentive to choose y-axis over x-axis. That incentive comes from S1 square plus S2 square, so that the variance of both of them reduces. Okay, there is a raised hand. So yeah, go ahead.
So why are you using all these squares? Why can't you use absolute of mu1 minus mu2 by
Because
S2?
because finally we would be differentiating stuff, and differentiating squares is much easier than differentiating absolute values.
I feel it is we have to take absolute values. Sometimes we take differences, we get minus. That's why to neutralize that with squares.
No, we can take the absolute values also, right? We can take this one. We can take this one also. So this would always be a distance between mu1 bar and mu2 bar. But we don't generally take that, because whenever we take square, when we differentiate, that gives us a easier formulation to work with.
Sir, can I share my understanding, sir, regarding that squares?
Sure. Go ahead.
It seems like whenever we square some value, then the weightage of that. So if it is larger variant, like example, larger variance, then the weightage of that increases. So for smaller value, when you square, the weightage of that decreases. So that is how, like, for larger values, we need to give more weightage. For smaller values, give lesser weightage. So that is where sometimes squaring helps.
That is not entirely true, because if your, let's say if your difference is, I mean this difference is less than 1, then squaring will actually reduce that value. Somebody is now asking why not use to the power of 4th and square. You can go ahead and start using, no issues. Okay. I mean nobody has used it till now, but you can go ahead. So yeah. So
Sir, now
Yeah.
I've understood what your explanation, but why is it like we are doing all this because we want to reduce x and y to only y axis and then project all our instances only on one axis? Is it
Yes, precisely. We are trying to reduce the dimension from 2 to 1.
Okay, then how is this related to something you explained, sir? Like initially you explained something C minus one. I'm
Huh.
not able to.
So here there are two classes, right? Class 1, class 2. So what I had said was, if you have C classes, then you can maximum go up to C minus 1 dimension. So here there are two classes, so that is why you can go up maximum to 1 dimension.
Okay.
Yeah. Okay, so this is this is the intuition behind LDA. Now there is some dry math which is there. I don't know whether I should go through that. Okay, so because that involves a bit of vector differentiation and all those, but those are not part of the course. So let me just tell you certain things, and then I will,
Sir, can you just explain? This
Yeah.
is just two-dimensional data.
Huh.
So in case if you have 3 dimensions, how this equation will be? This optimization parameter.
So for that we can, we need to go to a vector or a matrix formulation. That would be easier. So I'm coming to that. Okay. Okay. And by the way, this is not for 2 dimensions, right? This is not for 2 dimensions. Okay, I see there is a problem here. This is not for 2 dimensions. This is for 2 classes.
Okay.
Okay, this is for 2 classes. Your mu1 and mu2, s1 and s2, they can be as long dimension as possible.
Okay.
Okay.
So in that case, that mu1 is a multi-dimensional.
Is a vector.
Multi-dimensional vector.
Yes.
Okay,
yes.
I got it.
Yeah.
So See, in machine learning, we have to imagine multi-dimensional vectors.
Yes. So but you raised the correct question. Okay. So I don't know whether I should say this here or.
Sir, sorry. Now, when we are talking about again classes and not dimensions, again that C and C minus 1 is little.
See,
confusing.
you have all your vectors x1, x2, x3, x4. Let all of them belong to class 1. Okay, and x5, x6, x7 and x8, let them belong to class 2. These are your 2 classes. Okay, and all of them are 100 dimensional vectors. Fine.
Okay.
Now all I am saying is, you can project this x1, x2, x3, x4, x5, x6, x7, x8 to y1, y2, y3, y4, y5 up to y8, and all of them will be R of 1. They will be points.
Okay.
Okay.
So it will be like only in one dimension.
Yes.
So the 2 classes of 100 dimensions are converted to 2 classes of 1 dimension.
1 dimensions. Yes.
Okay.
Okay.
And so in that case, the classes is not changing. The dimensions will change, and it is related to the classes.
Exactly.
Number of classes.
Precisely.
Okay.
Precisely.
Got it.
Okay. So now, so for okay. So means mean, as somebody said also, like mean for a vector would be a vector itself, right? So mean would be mean of mu. So how do you define mu I? Let's say you would define it as summation of xi, sorry, summation of x, where x belongs to all the classes Ci, divided by 1 by Ni. That is how you would define mean. So all these would be some R capital D dimensional vectors, and therefore mu I would also be a R D dimensional vector. Okay, so this is how means are defined. There is another thing, I mean the denominator had the covariance, I mean the denominator has the variances. So when you are talking about vectors, you define something known as covariance, and it is defined as follows: Si, so this is basically a matrix of R D cross D. Okay, right, if something is wrong again with this, don't know what, but okay. Yeah, this is R of D cross D, this is 1 by Ni, summation x belongs to Ci, x minus mu I into x minus mu I transpose. This is how covariances are defined. Okay. This is Si square, okay, if you can call that. So this is Si square, which is 1 by Ni summation x. So you take all the points for belonging to a particular class, and you do this. So this is a vector, x is a vector, mu I is also a vector, so x minus mu I is a vector, and this becomes a D cross D matrix. Okay, this is a D cross 1 vector. Once you take a transpose of that, that becomes 1 cross D. When you multiply, you get a D cross D matrix, and you sum that for all the points belonging to a particular class, you will get the variance of the particular class. So now you know how to calculate this mu I for each of the in the numerator, and you know how to calculate the denominator also. Okay.
Sir, just
Yeah.
one fundamental question.
Yeah.
This LDA is only for classification problems, right?
Yes.
Not regression. Only for classification.
It can be used for regression, but that is way outside the scope.
Yeah, yeah. But yeah, in
In this course,
it's
it's only for classification.
Okay, okay. Sir.
Yeah. Okay, so we come to this, and then there is a lot of maths. I mean, I won't go into those details, and so you do, I mean, then you solve this, I mean, then the formulation is actually, you write this one, you write this particular thing in a matrix notation, and once you write it in a matrix notation, then you solve it by differentiation. Once you differentiate and solve it, you get the value of W. Okay, so I am not going into that. Maybe if somebody wants, I can also cover it, but I don't think it is required also. I mean, whatever I have taught, even that was not required, I feel. But anyway, I just wanted to give you a feel about why these two terms are there, and an understanding about how it will be solved. I mean, some understanding about how it can be solved. Of course, I won't solve it. So
Sir,
yeah. Yeah.
Okay, let me state, I think I'm getting some clarity now.
Okay.
The whole objective of LDA is a multi-dimensional data to single-dimensional vector, separator, right?
No, that is
so,
only for two classes.
Two classes.
Yes.
Okay.
Yes.
So linear, okay, the word linear is coming into picture because that is a linear multi-dimensional vector. Right? Linear.
No, because you are taking your points x and you are multiplying that with a vector in this case, which is W,
So
and because of that it's a linear combination of your x's. That is why it is called linear.
Okay. So basically generalizing from 2D to multidimensional data, we can say that finding that linear vector, which actually helps classify the multidimensional data very well.
Yes.
Right. Okay.
Yes.
Okay, sir. Right.
Yeah. So, okay. So this will be it. I won't go much into the details of LDA. So finally, it becomes a bit of mathematical jugglery and all. So I won't go into all those details, but I'll take some questions on LDA and 1 or 2 questions on PCA also, and then I'll stop the session. Okay.
Sir, like what is the basic difference, sir, between PCA and LDA? Like both
Yeah.
reduce the feature, right? So then, but what is that is differentiating other than supervised, unsupervised?
Oh, other than unsupervised and supervised, there is no difference. I mean, yeah. Let me complete. So, see, okay. So let me put it this way. So, see, when you are, I would ask you to think very intuitively on this. So, when you are looking at an unsupervised problem setting, okay. So that means you don't know which points belong to which class. Now, when you don't know which points belong to which class, when you are doing PCA, let's say when you don't know what you are, which points belong to which class, the only way in which you can preserve the quality of your data is to say that, okay, my data has this much variability. I would come down, I would reduce the dimensions, but at the same time I don't want it to reduce so much that all the variability in the data is lost completely. Am I making sense?
Yes, yes, sir.
Yeah. So when you think about this, I mean, this is the intuitive way of thinking. The mathematical way of formulating this is to, okay, I want to reduce my dimensions, but I want to keep the variance of my data as I want to keep the variance of my data as close to the original variance as possible. Because when I keep the variance, that means the variability that was originally present in the data is also maintained.
Yeah.
Right?
Sir,
Yeah.
sir, as I understood it, see, LDA is a full-fledged classifier. We are
Yes.
discovering that vector which actually classifies. Problem
Correct.
is solved in the LDA. Classifier
Correct.
problem solved.
Yes, yes.
But in PCA, we don't look at the label attribute. We only look at the input feature vector
Yes.
and then try to reduce the dimensions to as few as possible. Instead of 100, maybe 2, 3, 4,
Yes.
less than 100.
Yes.
So, but the PCA, the problem is not solved. We only reduced the dimensions. So, in PCA can be used for both regression as well as classification, right?
That LDA can also be used, but the only you are correct. You are correct in that sense that PCA LDA can give you a classifier. Okay,
Yeah.
LDA will actually give you a classifier at the end of the day. So in that sense, LDA LDA solves the problem for you. But PCA is actually a much bigger thing in that sense, because let's say even if you don't talk about classification and regression, suppose you don't have the labels, okay, you are clustering, let's say. So your clustering means you have been given points like you have been given a class of points here, you have been given a class of points let's say okay, you have been given a class of points here, let's say. Okay, now of course this looks very simple because it is in 2 dimensions. Now PCA what it will try to do, it will try to do this, so that the variance of both of them remains constant. This is your entire data set, right? So if you try to reduce the dimension of PCA, of course 2 to 1, then PCA will give you this particular it will project it on the y-axis in this case, and then your clustering becomes very simple. Now of course imagine this when you have 1000 dimensions and you are coming down to 100 dimensions, then all your computations, everything become very much 10 times simpler, correct? And however, if you knew the labels of this and this, then you could have done LDA, but somebody would have to sit and label the data for you. You can just take data and do PC on it, and you will reduce the number of dimensions.
Yes, sir. But as I understand, PCA's focus is only dimensionality reduction, but
Yes,
actual problem of classification of regression is afterwards,
afterwards, precisely. Yeah,
right? Whereas LDA, that classification is built into the process itself.
correct, correct, correct.
Okay. Right.
Yeah. So I hope that was clear. Then coming to some very basic questions. Okay. So the first question is aim of LDA. What is the aim of LDA? So can somebody say, okay, let me go through one by one. Minimize intra-class variability. Intra-class means between, no, intra-class means within a class. Okay. Minimize intra-class variability or maximize intra-class variability. Which one is correct?
Minimize.
Yes, because you saw here that here you are yeah, there is some noise. Yeah, okay. So you saw here that you are trying to minimize the intra-class variability. That is why you gave this S1 square plus S2 square in the denominator. Okay. So that is one. And minimize the distance between the mean of the classes or maximize. This I have already told. So maximize the mean, the distance between the mean of the classes. Okay. These I think were questions in the last run of this course. So I'm not sure whether your assignment questions will also be similar to these. So okay, now is an interesting question here. We have two classes in a data set with mean 0 and 1 and variance of 2 and 3. So let me draw normal distributions only. So that would be simpler to understand. Let this be 0, let this be 1. Okay. And I have a mean of 0 and variance of 2. So variance of 2 may be like this. So if this is 2, then it is like this. Okay. And you have another class which has a variance of 3. So 1 minus 1, so it will go somewhere like this. Somewhere like this. Suppose these are your two data distributions. So what do you think? Will LDA be able to classify them or not? Suppose these, yeah, because there is a huge overlap in between these two. These are distributions, right? These are distributions, mean of 0 and 1 and variance of 2 and 3. So LDA won't be able to classify them properly. So LDA will definitely not be able to classify them perfectly. There will be some overlap. Okay. Okay. Then we have two classes. Now it has changed. Now the data set has mean of 0 and 5 and variance of 1 and 2. So one mean is here 0, the other mean is 5. You have a variance of 1 and you have a variance of 2, which is 3 and 7. So I am just marking the variance also, but so this will be something like this and this data set will be something like this. Yeah, now what do you think?
The LDA can classify themselves since there is only a little bit of variation overlapping.
So this is a tricky question in that sense. So of course this is not true, right? I mean LDA will definitely not be able to classify them. You cannot say that, because there is I mean these distributions are actually separated out. However, you see that there is still a little chance that you end up with data points in this region. So if you end up with data points in this region, then LDA won't be able to classify your data. So the answer would be LDA may be able to classify them perfectly. It depends on the data points that you are getting from these two distributions, from these two classes. It depends on the data. You cannot say just by looking at these two data distributions that LDA will definitely be able to or LDA will not be able to. Both of them is incorrect. Okay, I hope I made sense here.
Yeah, because just a minute.
Yeah.
Can you go back to here? So basically, it is a distribution of data. So
May.
it might
Might.
be separated out.
Yes, precisely. So then the final question on LDA. So you have the two classes, the plus and the minuses, and you have different lines which are shown. Now which one would you think is the correct line for projecting the data points? Blue, green, orange or red?
Blue.
Green.
So blue one.
Blue one, and somebody said green.
Green, I said.
Okay, so let's talk about green first. So if you are trying to project on green, you will have to project it in this direction, right? Okay. So this will be your projections, and this will be the plus projections, and this will be the minus projections. Okay. So there is an overlap here. This part is overlapped. Okay. So I'll rub this off now. I hope this was clear. Now let's talk about the blue line now.
Had it been blue,
Yeah.
then
Yeah, I'll draw the blue line now. So let's say you have blue here, and you have blue here. You have more or less negatives here and negatives here. So the overlap at least is much less in blue.
yeah.
So the correct answer
So-
would be blue.
Yeah. So the rationale is we have to choose that line where the overlap is minimal.
Minimal, yes. Because that is why you chose here in this case you chose this line, right? You chose line 1 instead of line 2, or you chose in the other example which I talked about at length, you chose the y-axis instead of the x-axis,
Yes.
because you don't want it to overlap, because as you said, your classifier, it will give you a classifier, so your classifier itself will be wrong, right, in this case if there is overlap. Okay, so these are the questions on LDA. I'll probably write one or two more questions. Let me check my notebook. Okay. Okay, so let me give you a question on k nearest neighbors. So suppose your data is corrupted with noise. How can you improve the performance of the KNN algorithm? Option 1 would be increase K. Option B would be decrease K. Yeah, you can tell me between either of these two. What should you do when there is noise? Should you increase or decrease K?
Decrease K.
Okay.
Decrease K.
Okay. So there are two.
Increase K.
Yeah. So
Increase K only. Like,
yeah. So there are two options. I've got both the answers. So let me give you an example. So k nearest neighbors means you are not training anything. Okay, k nearest neighbors is probably the only algorithm in machine learning where you don't need to train. Okay, you just test time only will work. So what is happening is, suppose you are doing classification only. Okay, suppose you are doing classification and you have noise in your data. Noise means label noise in this case. Okay, let's say you have label noise only. So suppose you have these many points. Okay, oh, I drew all of them in the same class. Oh, okay, no, let me draw something like this only. Okay, and this, the circle one, this one is your test point. This was the true distribution. I mean, this was the true data or whatever. You added noise to this data, and now your training points have changed in such a way that it becomes something like this. This is your test point again. So of course this won't change because this is given to you during test time, and this point has now changed to this. Rest all points remain as it is. So this point becomes of a different class, and unfortunately this is your closest point to the test point. Okay. Now because of this noise that has been added, you will now misclassify this point, right? If you take k equal to 1. If you take k equal to 1, then you will choose this point, the closest neighbor, and that says class x, and therefore you would also predict this point to be class x. However, if that actually in the true distribution this was also in the same class, I mean this was also in the dot class, if you may call that.
Hello, sir.
Yeah.
Are you sketching something we are not able to see?
No, I am not sketching anything right now.
Okay.
So this particular point is actually of class 1, but due to noise it has become of class 2, let's say. Now this is class 1 and this cross is class 2. Because of k equal to 1, you are choosing this point, and you are also saying that your test point is class 2, but that is only because of the noise that was added. If you had taken k equal to 3, let's say, then you would have chosen the 3 nearest neighbors and you would have taken the majority vote among the 3, and then even with the noise you would have predicted the correct class. Am I making sense now? Is it clear?
Yes, sir.
Yeah, so that is why whenever you have noise, you need to increase your k. If you decrease your k, then your error will increase because of the noise. Okay, so the last question, of course I did not go through PCA, but there was one question about PCA last time.
Sir, one question.
Yeah.
Here we are talking about noise in the labels only.
Yeah,
Right?
yeah.
But in any instance, did we consider noise in the input space features?
Input features if you have noise, right?
But I mean, just my comments are just general question. In the entire machine learning, are we considering about noise in the feature space?
Let me think. Noise in the feature
Because in the regression also, I think we are more focusing on that epsilon is noise in the output, right? Label, not in the input.
Features, you generally don't expect your features to be noisy, because see, machine learning, the thing is there is an underlying process which is generating something, okay, and when it is generating something, that something you are trying to model. I mean the process which is generating something you are trying to model by means of a machine learning model, okay.
Yes.
So that while generating the data points only, it will give there may be some noise added to it, correct?
Yes.
So that is why you generally always talk about label noise. Features is something which is in your own hands. You are given a data point, you are extracting features from it. So it doesn't make any sense to talk about noise in the features. If you are thinking that your features are not important, nobody is stopping you from changing the features completely.
Okay. Great.
Yeah.
I think the assumption we have to make is that features are what are features. That's it. Only the noise or the variability comes in the labels.
Labels, yes.
Yeah.
Precisely.
Okay, great.
Yeah. Okay, so then I'll talk about okay. Okay, so let me talk about certain features of PCA, and I'll ask whether they are true or not. So the first question is, PCA is a supervised method. Is it true or false?
It is false because for computing PCA we don't use the label at all.
Precisely. So that is false. Okay. The next is, I mean, this is the definition of PCA. So of course this has to be true anyway. So it identifies the directions that has maximum data variance. So is this true or false? Okay, somebody is saying yes. So yeah, this is true. This is how PCA is defined. Okay, so the third question is, the third point is the maximum number of principal components less than equal to number of features. Is it true?
Yeah, certainly. That is
Yes, yes.
C minus 1.
Yeah. No, C minus 1 was about LDA. PCA has no such C minus 1 thing. Okay. So, you can think of maximum number of principal components being less than the number of features is, if you had equal to the number of features, then you wouldn't have done PCA in the first place, right? So that is the first thing. And the second point is, and because it's a dimensionality reduction thing, therefore it will reduce the number of features. Okay.
Sir, based on this one, right, sir, I
Yeah.
have one question.
Yeah.
So if for PCA, if we kind of reduce features, means we are reducing overfitting, right, sir? So in that case,
overfitting.
I just want to know, like, what is, like, how is PCA related to regularization? So if, is it like,
PCA is, how is it connected to regularization? Okay, that's an interesting question. So PCA, as far as I know, see, regularization or overfitting, though that is talked about in a different aspect. Okay, it is talked about in a case that, okay, my model is trained in such a way that the training error becomes 0, but it is not generalizing to good test distribution. I mean, it is not generalizing to the test data. My training accuracy is 100%, my test accuracy is 50%. That is a case of overfitting. In PCA, you have no training involved. There is no modeling involved in PCA.
yes, but there will be reduction of features, right? So it means we'll be selecting only significant features here.
You will be selecting significant features. For example, I mean, I'll tell you an example about what will happen. So I will give you an example. Okay, let's say you have you have designed a classification problem, okay, where you have two features. One is, let's say, okay, one is, let's say, income of a person. Okay, that is one feature that you have. Apart from this, you also have a feature, okay, this one in income of a person in rupees, income of a same person in US dollars. Okay, you understand this, right? You can have two such, nobody is stopping you from having these two features.
Yeah.
Redundancy can be considered and then removed.
Yes. So what PCA will do is, PCA will understand that this feature, if you take, then this feature is not adding anything extra for your classification. Okay, it is just a scaling of the of the two.
Or we can say, sir, if the two features are highly correlated,
exactly,
then one of them is unnecessary.
So this is these two features are highly correlated, so PCA will throw one of them out. That is the only thing that PCA will do.
So means, at least my understanding was, sir, like PCA will not only remove redundant features. That is something which is done by something Pearson, correlation coefficient, and some other.
Right.
But here PCA is mainly used to reduce. That is mainly used for feature reduction rather than feature selection or filtering. So here for reduction, it will reduce like from 100 to, let's imagine, to 20.
Yes.
So it's not like it is just removing the redundant features. It is also kind of like combining 2 or 3 features and creating a new feature with which has significance of all those things in the weightage of it.
Precisely. So in this case, what will happen is you are perfectly correct. So let's say you just have 2 features, okay, and suppose you have 2 dimensions, and you are trying to come down to 1 dimension. Then PCA will combine these 2 features in such a way that PCA's weights, I mean the weights that PCA will assign to all of them, if you can call them weights in that sense, what it will do is it will put a weight of 1 here and a weight of 0 here. I mean that also PCA can do. And if you give features like this, PCA will do precisely this. It will remove this feature completely. This feature will be removed completely. You are correct. You are correct. Yeah.
Okay, go ahead, sir. Go ahead.
Yeah. So that is, I mean, that is the same way. I mean, I gave you this example because it is, what can I say? Because it is easier to work in this way. I mean, it is easier to give for me to give an example like this. Now, what you are correct in saying that PCA, what will it do if you have 100 features? Let's say it will come down to 20 features. Okay. So once it comes down to 20 features, then your classifier will also be, you will have a simpler classifier. That you can say. If you will have a simpler, you will have a simpler classifier, maybe because of that simpler classifier your regularization will automatically happen. Because what I am trying to say here is, if you have a 100 dimensional input, then your classifier works on 100 dimensions. If you reduce it to 20 dimensions, then your classifier will work on 20 dimensions. And this is a much simpler classifier. So in that sense, you might consider that, yeah, this simple classifier will be less prone to overfitting than this classifier. You can say that. Okay.
It's similar to like that L1 and L2 regulations, which will kind of keep significant features and remove the unsignificant features. So it's a
no, but I don't really want to say it like that, because you see what happens is, okay, first of all, is L2 and L1 regularization, I think it was taught in regression, right?
Yes, sir.
Okay, so I can show that now. Okay, so let's say you have y minus w transpose x whole square. So this is your regularization least squares, this thing, the least squares formulation. Then what you do is you do this thing, right? This is L2 regularization. This is familiar, right? Now yeah, okay, so now here what you need to understand is, here when this problem is solved, you are solving towards a particular objective. You already have this y here. Am I correct?
Yes.
You are trying to get that w which gets very close to y, and at the same time which has a 2 norm which is also very less. I mean, this also needs to reduce, this also needs to reduce. PCA in the entire formulation, you won't find anything of that sort. You will just see that I want to reduce the number of dimensions. I want to reduce the number of dimensions so that the variance or the total data variability that was present before is also preserved after PCA. That is it. That is the only way you should think about PCA. And I would not suggest to talk about overfitting in terms of PCA, because PCA is an unsupervised method, and overfitting is generally always considered only when you have some overfitting is always important when you have some training issues. The mismatch between training and test is what leads to overfitting.
Yeah, yes, sir. I agree with that. So overfitting is actually related to the model building.
Yes.
Actually, in PCA, we have not even gone into the model.
Model,
We are looking
precisely.
at the input data itself. We are fusing in input data to as many few dimensions as possible.
Yes. No, but
Yeah.
she is also correct in the sense that because you are coming down to 100 to 200 dimensions, in some sense this thing is, I mean, Yeah, so I can give you one example here. So suppose you have 100 features. Are you still with me who asked me the question?
Yes, sir.
Yeah,
Yes, sir.
yeah. So if you have 100 dimensions, you can still have a regularizer, right?
Yes.
And that regularization would help you, let's say, select 20 dimensions. All the other W's will go to 0. That is what that is where you are coming from, I believe.
Yes, sir.
Now suppose you have redone PCA and come down to 20 dimensions. And then again with these 20 dimensions you run this problem. And then because of this regularization you may end up selecting only 12 dimensions.
Okay.
So the classifier building comes after PCA. PCA can help you make simpler classifiers. The classifier building and overfitting is concerns itself with classifiers building, not the data distribution.
Okay, sir.
Okay. Yeah, so that was one. Yeah, okay, so that is it. I did not have any other thing to cover today. So I hope I made some sense about LDA and some questions about PCA. So if you don't have any more questions, okay, two more things that I have to do is, yeah, I will cover these three questions next class. So yeah, so if you don't have any more questions, I'll stop the session. So yeah.
Thank you so much.
Thank you.
Thank you.
Sir, when will be LDA perfectly aligned with mean and the variance, sir?
LDA perfectly aligned with mean and variance means?
The overlapping.
Huh?
When will it will be perfect? It never be perfect or maybe every time?
No, not every time. Of course, not every time. In certain cases, for example, I showed this example, right? Like this example which I showed. If you
Yeah.
you can do LD on this. You can do LD on this, but you will have some error. All classifiers no classifier will ever give you 100% accuracy.
Yes.
That's what I'm trying to say here basically. But in certain cases like this, then LD is a very bad choice. It won't be able to classify them at all.
It won't even overlap anywhere. That's it is. Okay. Thank you.
Yeah. Thank you, everybody. We'll meet again next. Yeah.
Okay, sorry, sir. One last question regarding the notes, sir. One thing is not clear. So, in the notes regarding feature selection steps, not sure if you will be able to open it. In the page 35, they gave like search strategies and evaluation strategies. So in search strategies, they mentioned like optimum strategy, heuristic, and randomized.
Okay.
And evaluation, they mention as filter and wrapper. So I wasn't clear what is that search strategies, optimum, heuristic, and randomized.
Okay, this is about which part?
About feature selection. Let me see, sir, which it was in part B, feature selection, lecture
I
B.
don't have the access to the notes actually, so that's an issue for me. Okay, so feature selection, right? Feature selection means what? You are going ahead and selecting one, not feature removal. You are selecting one feature after the other.
Yes.
Right. So, the way you would do it is, you would go on adding the features, and when your accuracy doesn't improve anymore, then you would stop adding any more features.
Yes.
That's what I understand. Now, what are the three strategies? Optimized,
heuristic, and randomized. These are the three feature search selection search strategies. So first you search and then you evaluate those feature selection.
Okay, randomized means of course you select at random which features you want to choose. The order in which you want to choose the features, you can to choose it randomly. That is one. The other way in which you can choose that is feature removal.
That's the only one I could visualize there, like random, like
randomized, yes.
And then think if it is adding some reducing the error or not, and then decide to keep it or not.
Yeah, and the others they were not discussed in the class, is it?
I think not Sure, sir. Little bit might be was explained regarding optimum, but couldn't at least couldn't follow that, sir.
Okay, okay. Let me try to get hold of the lectures, and that will be the first thing that I will be talking about next day. Then maybe. Okay. Lecture notes I will need to get hold of. I don't have access to it as of now. So once I get access to it, I will go through it and I will let you know next class surely.
Oh, thank you, sir.
Yeah. Okay. So if you don't have any more questions, I'll stop the session. Yeah. Okay. So thank you. We'll meet again next Tuesday. Thank you.
Thank you, sir.
Thank you, sir.